slide. Perfect. As we're all very much aware, in the last 5 years, the use of AI for science and scientific discovery has surged. Arguably, one of the most notable examples is AlphaFold, which has completely revolutionized the field of protein folding. So much that in October last year, the Nobel Prize in Chemistry was awarded to David Baker, Demis Hassabis, and John Jumper. And as if one Nobel Prize wasn't enough, that modern-day machine learning has just become so strong was underlined by a second Nobel Prize, the Nobel Prize in Physics, awarded to John Hopfield and Jeff Hinton. But AI hasn't just revolutionized the field of protein folding. It's also rapidly advancing various other fields too, such as drug discovery, materials design, and of course, we're going to talk about today, weather forecasting. Let me give you a very brief history. It all started back in 2018, when the first serious efforts were made to compare AI weather forecasting models to traditional numerical physical baselines. In 2019, Jonathan Wayne and colleagues showed that for the first time, AI weather forecasting models can be skillful up to multiple days. In 2020, Stefan Rasp and colleagues created WeatherBench, which was some kind of standard benchmarking data set for weather forecasting models. At the time, such a standard benchmark didn't really exist. The development of WeatherBench really started to drive the development of machine learning models for weather forecasting. The tipping point came in February 2022, when Keisler showed that a graph neural network outperformed NOAA's GFS, the global forecasting system, at 1 degree's resolution. And the big breakthrough came later that year, when Pangu Weather finally outperformed ECMWF's HRES, the gold standard numerical NWP, numerical weather prediction system, at 0.25 degrees resolution. Now, this was really a big deal. It's called everyone's attention, including the attention of tech companies who started to work and heavily invest in this space, which eventually led to the development in 2023 of GenCast. Now, for the first time, GenCast didn't just outperform IFS HRES, but the entire IFS ensemble. Finally, in 2024, ECMWF launched AIFS, their AI forecasting system. I think that ECMWF, an organization, an institution that's world-renowned for their traditional numerical approaches, starts to heavily invest into AI models, to me really speaks to the potential that machine learning models have in this space. Now, I think all of these developments are amazing, they're incredible, and really excited about them. It is just a shame that these developments, these advancements, are mostly limited to the setting of medium-term weather forecasting. Don't get me wrong, medium-term weather forecasting is really important, but there are many more other important forecasting tasks out there, such as air pollution forecasting, or more generally forecasting the composition of the atmosphere, ocean wave forecasting, sea ice forecasting, or more generally forecasting the state of the ocean at various levels of depth. Whereas the current range of models is extremely impressive in their capabilities, unfortunately, for the most part, they are limited to just one setting, which is the setting of medium-term weather forecasting. What is needed is some kind of unified approach that can extend these impressive advancements for medium-term weather forecasting to other forecasting fields too. This is the main motivation behind Aurora. The key idea behind Aurora is the following. First, we're going to take a single neural network and we're going to train it on a large body of Earth system data. This is called pre-training. And by a large body of Earth system data, I don't just mean a large data set like ERA5, which is big, but I mean as many data sets like ERA5 as one can find, which would be a mixture of analysis products, reanalysis data, forecasts, reforecasts, climate simulations, you name it. The purpose of pre-training is to let the neural network learn some kind of general purpose representation of the dynamics that govern atmospheric and oceanic flow. Once the model has been pre-trained, And this is really the crux, the reason why we're doing this project. Once the model has been pre-trained, the model can use the learned general purpose representation to efficiently adapt to new domains, to new tasks, to new variables. This is called fine-tuning. And the idea is that the model can really use the learned representation to perform this adaptation efficiently, which requires often little data. This means that fine-tuning is typically fairly cheap and data efficient. In contrast, pre-training is often really expensive, requires lots of data and costly. You can view pre-training as some kind of one-off cost that you have to pay, but once you've got a pre-trained model, you can relatively cheaply fine-tune it to a variety of applications, perhaps even novel applications. Models that can be pre-trained and then fine-tuned were often called foundation models, which is why we say that we intend Aurora to be a foundation model for the Earth system. Now, the idea of pre-training and then fine-tuning is definitely not novel. For example, it's been incredibly successful in the space of large language models. With Aurora, our intention is to bring the pre-training fine-tuning paradigm to environmental forecasting too. In the remainder of this presentation, I would like to say a few things about pre-training to sort of briefly outline what we did on that front. And then I would like to zoom in onto one particular fine-tuning application, which I think is most interesting for this community. Let's start out with a few words on pre-training. But first, what is Aurora? What does it do? Very concretely. Very concretely, Aurora is a single neural network that can predict the global state of any collection of variables at any resolution 6 hours into the future. And it does this based on the state at the current time and the state 6 hours ago. When pre-training, we train this one-step prediction, so the prediction 6 hours into the future, on a large collection of data sets. The variables that we primarily consider during pre-training are listed in this table, which is subdivided into surface level variables, which are variables defined only at the surface, of course, and atmospheric variables, which are variables defined throughout various levels of the atmosphere. Surface level variables include humidity, temperature, UV component of wind speed, and the air pressure and sea level. And the atmospheric variables include wind speed, again, temperature, specific humidity, and geopotential. Now, the following table, the data sets that we use during pre-training and all data scaling studies are listed in this table. And here you can see that, as I alluded to before, we used a mixture of reanalysis data like RF5, but also forecasts such as HRS forecasts, and even forecasts by the entire RFS ensemble, GFS forecasts. There are even reforecasts in there for GEFS. There are analysis products in there like GFS T0, 2 climate simulations, CMCC and ECMWF. They're from CNIP 6, and NAR2 is in there as well. Now, together, these data sets comprise 1.2 petabyte of data, and that's a lot. Our intention was really to expose the model to as much and as diverse data as possible. We pre-trained the model for about 150,000 steps in 32 A100s, and that took about 3 weeks in total. Okay, so once we obtained a pre-trained model, we proceeded to fine-tune it to 4 different applications, which are shown on this slide, which are air pollution forecasting, ocean wave forecasting, tropical cyclone track forecasting, and very high resolution, 0.1 degree, weather forecasting. The visualizations here show actual predictions by the model. I think these pictures are really cool. I didn't make them. Credits go to my colleague, Megan. In all of these applications, we've been really careful that the resulting fine-tuned model is operational, which means that the resulting fine-tuned model, in principle, could be deployed in a real-time system. And for this, you have to be a little bit careful. For example, if you train your model on RF5, then the resulting model cannot be deployed in a real-time system because RF5 isn't available in real time. Similarly, say for tropical cyclone track forecasting, they make the distinction between early and late models, which are very strict requirements on when the forecasts have to be available. So we spent quite some effort to get these details right. Now, I'd love to talk about all of these fine-tuning tasks in detail because I think they're all really cool. But I think in the right of this presentation, I'd like to zoom in onto the first one, which is air pollution forecasting. In this fine-tuning task, in addition to the collection of meteorological variables that I outlined earlier on the pre-training slides, Aurora models levels of particulate matter near the surface and the concentration of various chemical species throughout the atmosphere, which are carbon monoxide, nitrogen oxide and dioxide, sulfur dioxide, and ozone. We train the model, we fine-tune the model on an analysis product from a system called CAMS, Copernicus Atmospheric Monitoring Surface. CAMS is an extension of IFS. And by an extension, I really mean that CAMS is coupled to IFS. This coupling makes the whole thing really expensive. CAMS is about 10 times as expensive as IFS itself. And in fact, CAMS requires about 60 node hours of computation per hour liter. In contrast, after we fine-tuned Aurora, the model can make predictions at the speed of about half a second per hour lead time on a single A100 GPU. So that's a considerable speed up. After we fine-tune the model, of course, we want to validate its predictions to see how well it actually does. And for this, we compare its predictions to predictions by the same system, so forecasts by CAMS. So not to make this too confusing, this means that we use CAMS in two different ways. We use the analysis product as a ground truth, and we use that to fine-tune the model. And we use forecasts by the same system as a baseline. Fine-tuning a machine learning model on air pollution data is challenging for a variety of reasons. The first is that air pollution data is distributed heterogeneously in clusters near cities, and it's incredibly spiky, by which I mean that it has a really large dynamic range because of the concentration value. So the values span many orders of magnitude, from really tiny to really small. In addition, these variables are often driven, strongly affected by anthropogenic factors, such as human emissions. These are really difficult to forecast. The fine-tuning data which we use, CAMS analysis, unfortunately only goes back to 2015, I think. So that means that our training data in this setup is actually really scarce. On top of that, CAMS undergoes yearly updates, which can significantly improve, but also alter the system. This means that our training data isn't just scarce, it's also highly non-stationary. Nevertheless, despite these challenges, we were able to successfully fine-tune a model on this data. And as you can see, at least visually, the predictions line up with the ground truth. But how well does the model really do? Let me show you the full results. Now, don't worry if this is a lot. Let me step you through it. Okay. Somebody started drilling in the house next to me. Can you hear this, or am I still?
It seems like it's filtering it out. You sound good.
Good. I'll just continue. If it becomes annoying, just let me know. I'll just proceed. Okay. The results as presented here are presented in the form that we call a scorecard, which shows the performance for every variable involved in this experiment. At the bottom, we see the performance for all the surface level variables. And on the top, we see the performance for all atmospheric variables. The x-axis shows the performance by lead time, so how far into the future we forecast. For the atmospheric variables, the y-axis shows the performance by pressure level, so how high up in the atmosphere we are. Finally, the color indicates the performance of Aurora relative to CAMS, where blue means that we're better, white means that we're equally good, and red means that we're worse. Aggregating all the squares, Aurora is competitive to CAMS, by which I mean within 20% RMC, on about 95% of all the squares, and better than CAMS on 75% of all the squares. At 3 days lead time, so forecasting 3 days into the future, Aurora is competitive to CAMS on all squares, and better than CAMS on 86% of the squares. Now, I'd like to make two remarks about these results, which I think are interesting. The first thing that stands out is that Aurora tends to lose out to CAMS on the air pollution variables at the 12-hour mark near the surface. And it's not exactly clear what's happening, but I think a few things could be going on. The first is that CAMS doesn't actually assimilate real-time emission observations. This means that the air pollution variables, which are most affected by human emissions, which tend to be pollution variables near the surface, are actually really poorly assimilated. And because the variables are poorly assimilated, this means that the analysis product is more biased towards the forecast, which biases the results in the direction of CAMS. In addition, AI weather forecasting models tend to exhibit overly smooth predictions, which is also the case for Aurora, which is often referred to as the spectral bias of machine learning models. And this effect is particularly noticeable at the 12-hour mark, so the early timestamps. Now, the second thing that stands out here is that Aurora tends to lose out to CAMS or ozone in the upper levels of the atmosphere. What's going on here, I think, is that there's actually a lot more ozone up higher than 50 HPA. Aurora does capture this ozone indirectly through the total column value of ozone, but perhaps to improve this, we could have included pressure levels higher up in the atmosphere than 50 HPA. Yeah. Okay. Finally, I'd like to highlight some technical details in this fine-tuning experiment, which may or may not be interesting. I think could be interesting. The first is that I actually lied about pre-training. Only in this fine-tuning experiment, we used a model which was pre-trained with a 12-hour timestamp. And the reason for this is the following. Some of the air pollution variables tend to exhibit really strong diurnal cycles, which means that the forecast 12 hours into the future is very much like the state 12 hours ago. And for a model with timestamp 12 hours, the state 12 hours ago is a direct input to the model. Whereas the pre-trained model directly predicts the target variable, in this fine-tuning experiment, we modified the architecture to actually predict a difference with respect to the current state or the state 12 hours ago. And which one we choose depends on the variable and depends on whether it shows a very strong diurnal cycle, like nitrogen oxides, or not, like ozone. We multiply this previous state with a modulation factor outputted by the network. And so the network can set this modulation factor to 0 if it thinks that predicting the difference actually isn't useful. Now, if you look at this, you may think, as we autoregressively roll out the model to make predictions further into the future, well, we could be multiplying the previous forecast by a factor which could be bigger than 1. And so the forecast may grow uncontrollably and eventually blow up. Yes, good observation, that's a risk. We didn't see this happening. It kind of just worked, which is perhaps remarkable. The second thing to point out about these air pollution, the second thing to point out is that when we normalize the variables, the standard deviation is actually a really poor estimate of the scale of these variables. And that's because they're positive, super highly non-Gaussian, very heterogeneously distributed. Instead, we normalize these variables with a scale estimated in a different way. What we did is we took per variable the maximum over space, and then we averaged that value over time. This scale turned out to work much better. Despite that the scale works much better, every once in a while there's still a huge outlier, which exposes the network to a really large value, which is an issue. And so to mitigate this risk, we decided to, after normalizing the variables, transform the variables by an input transformation before feeding it into the network. Since these variables are positive, a very natural choice would be to use a log transform. The problem with the log transform is that although it indeed successfully suppresses outliers in the upper range of the variable, these concentration values also attain really small values, like 10 to the minus 10, 10 to the minus 15, 10 to the minus 20 even. And so if you apply a log transform to this, you do successfully suppress the outliers on the upper side, but you're going to produce values like minus 10, minus 15, minus 20, which introduces outliers on the lower side. Therefore, the input transform that we used was actually a linear combination of the original value capped to 2.5, so capped from above to suppress outliers on the high side, plus a log transform, appropriately normalized, taken off the variable capped from below, 10 to the -4. But by taking a linear combination of these two, the input transform is still sensitive to the entire range of the variable. Finally, it's worthwhile to point out that we made various additional architectural modifications to really push the performance in this experiment. But I'm not going to dive into precisely what we did. You can see, read this in the appendix if you want, but yeah, I don't know how interesting that is. Okay, to summarize, in the last few years, the field of medium-term weather forecasting has seen some incredible progress, which is really impressive. It's just unfortunate that this progress, for the most part, has been limited to only medium-term weather forecasting. With Aurora, our intention is to use the pre-training fine-tuning paradigm to really kick the AI revolution in weather forecasting into the next gear by extending these advancements to other domains too. Now, although I'm really excited about this work, I should strongly emphasize that Aurora only scratches the surface of what's possible. Obviously, there's many more fine-tuning experiments that we can do, and quite possibly the setup of our fine-tuning experiments can also be improved. I'm sure the architecture can be improved in many ways. The pre-training protocol could be improved. We can always use more data, more diverse data, you know, kind of a game that you can play. But I'm really excited about this line of work, so I'm excited to see what the next few years will bring. Thank you.
Thank you so much for the presentation. I'm just going to go ahead and stop the recording.